Hello everyone. Today we're going to be talking a little bit about equilibrium of a particle. So the condition for the equilibrium of a particle that is originally at rest and remains at rest is said to be in static equilibrium. Equilibrium can also be achieved for a particle that has a constant velocity if it is originally in motion. So for a particle to be in static equilibrium, the sum of all forces applied at the reactionary must balance out. So their sum, in other words, their sum must equal zero. So the next thing that we're going to talk about is a free body diagram, also abbreviated as a FBD. So which is basically just a sketch of a particle that is shown as isolated and free from its surrounding. So basically a free body diagram is for us to be able to mostly just look at the important parts. And yeah, so things to show on a free body diagram, typically the important things that you want is the element or the particle, the dimensions and angles that were given, the external forces applied in the particle, which are typically given, reactionary forces acting on the particle, so the reactions, and there will be more on reactions later that we are going to talk about, which are usually unknown or assumed directions of each reaction. So here we have a linear elastic spring, and as you can see, the spring is having some force applied to it going downwards. So as you can see here on the side, this was right here, L of O, was basically that's where that was the original length of the spring. But once that force was applied, this is the extra length or where it came to at the end once that force was applied. So we have L final. And if we were to show that permanent deformation of this spring once some force was applied, and draw that out in a graph, we will basically have something that looks like this. So like that. And then from here, it starts slowing down. Let's make that actually a bit thinner. So we have a constant. Oh, let's zoom a bit. And then it starts slowing down until it basically doesn't change anymore. So right here, then from here we have not, and then no. Okay. And then we come back. Let's make that thin. Yeah. Okay, so what we have here is basically the force, how the spring is going to look once we start applying that force. And then as you can see, that force is going at a constant until it reaches basically the max that it's going to stretch while that force is being applied. And then once we take off that force, it's going to slowly come back to its original position. But as you can see, there is some permanent deformation. So this gap right here, once we take off the force from that um, spring, so it will not go back to its original length or shape. And what we call that is permanent deformation. And it probably won't be that visible like the first time that we apply that force, but as we go applying force more and more, that permanent deformation is going to become more visible. So the slope right here for this line, this linear line, is is basically just 1 over k, 1 over k. And right here, this axis right here is the force that was being applied. And this axis right here is basically the position that our springs at. And usually this is presented to as a S or as a triangle. So from all of this, um, we're going to take some things or some equations that you really need to memorize to help you find out uh, permanent deformation or stuff like that. So one thing that you have to really know or always keep is that force is equal to K over delta. Yeah. And we know that delta is equal to the final length minus the original length. And yeah, that's basically all that you need to know. Just another key thing is that to remember sign convention, that positive F stretches the spring, and when you apply a negative force, it will compress that string. So in this example right here, um, this was a positive force, which is why it stretched it. But if a problem ever says that it's gonna apply a negative force, that means it is compressing. So the force would be going upwards and making that spring compress even more. So now that we talked about that just a little, and I'm sorry if I got you a little mixed up, but we're gonna do an example. So our example 3-1, we have that the spring has original length of 6 inches. The spring stiffness is K equals 50 pounds over inches. And it's asking us how much force is required to elongate the spring to a total length of 6.5 inches. So what we're going to do is we're going to take these equations that we mentioned earlier, and we're going to use them in this example. So what I like doing first is I like highlighting or writing out things that were already given to us. So we have here that the original length of the spring was 6 inches. So as you can see right here, so I like writing that out. So we know the original length, or L of O, was 6 inches. Then we are given to us that the spring stiffness was 50 pounds over inches. So our K is given to be 50 pounds over inches. And from there, we know that we are trying to find how much force it is required to elongate the spring. So because we want a total length of 6.5 inches. So we know that L final, the final length, should equal to 6.5 inches. So with that, we're going to start off using this equation where, sorry, wrong one, that the force is equal to the stiffness times delta. And so if we were to rewrite that, we know that the stiffness is equal to the final length minus the original length. And then from there, we're simply just going to plug in um, all the all the information that we were given, because as you could see, we know what the stiffness is, we know what the final length is, and we know what the original length is. So all that we have to do to find the force is simply plug in everything that we already know. So we have 50 pounds over inches, and we have 6.5 inches minus 6 inches. So from here, we have 50 pounds over inches times 0.5 inches. And from there, we know that inches will be canceled out, and then we do 50 times 0.5. So that means that the force that we need to, that the force required to elongate that spring to 6.5 inches is 25 pounds. And just like that, we were able to find the required force to elongate the spring to a total length of 6.5 inches.